Okay, welcome all of you. Today's topic is tunnel diode. Uh, First, I thought that I should explain it to you through some pre-designed figures, but I will explain it in my own way. Okay, so without instead of saving times, it's better to understand the things so that you need not to go through this video again and again. Okay, so a few things I would like to clear in the beginning that tunnel diodes nowadays they are not being used. Okay, so generally its importance was for oscillator circuits, especially in microwave area. Okay, because of its negative resistance. Okay, in some portion this tunnel diode shows a negative resistance, and that's why it can be used as a source or oscillator. But nowadays generally these tunnel diodes are not being used because of many reasons, and one of the important reason is that other devices are far better, and they have replaced it, just like BJTs. They are not used now. Okay, very rare applications BJT might find. However, this BJT has academic importance because once you understand it, then you can understand other devices. That's why still tunnel diode has its academic importance. Okay, so it has its academic importance. That's why still most of the semiconductor device physics or solid state device uh, subjects, they have it in their curriculum. Okay, so let's understand how this tunnel diode works. So first of all, before I start, I would like to tell you that this is not a normal PN junction diode. Here N-type doping is generally 10 to the power. N-type or P-type, they are quite high. Okay, so if you have ND, that is of the order of 10 to the power 20 per centimeter cube. Likewise, Na, that of the order of 10 to the power 20. So that becomes this P and N type, that becomes degenerate semiconductor. So first of all, you should know what is degenerate semiconductor. So when you have very high concentration of holes, as you are increasing the acceptor doping, we all know that the Fermi level that will shift down from the intrinsic level. Okay, so this is normal P type material, and the doping level is normally generally it is 10 to the power 15 to 10 to the power 17. This is called the nominal doping. Less than this it is a light doping. Above 10 to the 17 it is called high doping. But degenerate semiconductors, they are you can say that very highly doped. So what happens is that this Fermi level, even that comes below the valence band. So Fermi level is somewhere here. So if anything, any material which has EFP in P-type material less than EV or EF in N-type material EC, then these semiconductors are called degenerate semiconductors. Okay. So here we have semiconductors, they are quite highly doped, very highly doped. So the energy band diagram, if you try to draw as a separate material, you will find that its Fermi level is over here. It is EV and it is EC. So this is the degenerate semiconductor, P-type semiconductor, and if we have EC and EB over here, then Fermi level in N-type semiconductor that goes even beyond conduction band. So that is EFN, right? Now, if they are forming a junction, of course, this is the individual Fermi levels. So what will happen is that they will try to align their Fermi levels. Okay, so with charge movements nearby the junction, they will have EF is equal to EFP is equal to EFN, right? And the band diagram will look like this. So this is EB, EC. Here you will have EC and EB. And in between, because the doping concentration is quite high, whereas of course the P and N that will be quite high, and that's why the junction width that will be quite small, very small W, which is proportional to 1 by Na plus 1 by Nd whole power 1 by 2. So that will be very small. This junction width will be very small, few nanometers. Okay, in fact less than 10 nanometers. So this is the given situation. Okay, in equilibrium. So till now we have not applied any bias. This is the condition. And from the definition of Fermi level, let's say if we talk about at T is equal to 0 Kelvin, all these regions are actually filled with electrons, isn't it? So let me draw it as, so all these regions are filled with electrons. Of course, because this region is also below Fermi level, so these areas are filled with electrons. Now internal diode, I had said that if the junction is width is very small, that condition it is already satisfying, then there will be a tunneling. But for tunneling there was another condition. Number one was very small width W. Number second was available vacant energy state on the other side or in opposite sides. Okay, or there are some carriers over here. If this on this side, if it is vacant, then there will be a tunneling, or otherwise from this side is filled and this side is vacant, then also this tunneling can happen. However, in this situation you can see that no tunneling is possible because all these states are already filled. So at zero bias the current will be, of course, zero. So at zero bias the current will be zero. Let's say we plot as V bias and ID. Now what will happen if we give a small forward bias? So as I have told that if you are giving forward bias, the whole this structure that will shift up, okay, in terms of energy band diagram. So the new energy band diagram will look like this. Let me draw it once again. So you will have new energy band diagram that will look like, so a little this will go up, EC will also go a little up, EV will also go little upside with small forward bias of around some few milli electron volts, sorry, millivolts. Okay, so now the situation is that these regions are filled, so it will find some of the region over here which is vacant. So now the tunneling will start. As you increase the forward bias, the whole energy band diagram that will start shifting a little up, and hence the current will increase because of tunneling. Okay, because the tunneling area, if you see the number of electrons, that is increasing. Okay, the density wise, if you talk about, this is increasing. The maximum will be when the Fermi level comes over here, just exactly in line of EV on the P side. If EFN is exactly equal to EV on P side, then there will be a maximum tunneling that is possible. So in this case, there will be maximum area which is contributing to the tunneling, right? And hence the current will reach to its maximum value. Why I am saying maximum? Because if you move it further, what will happen is that this EC is also moving, right? This EC is also moving up as you are giving the bias. Okay, EV is also. So if you increase the bias further, the situation will be something like this. Okay, so this is EC. Here you have Fermi level EF, P, EV, EC on P side, and if you have Fermi level which is above EV of on the P side, EFN, EC will be somewhere here and EV will be somewhere here. Now in this situation, what will happen is that tunneling is possible but only in small region. So if you see the common region, so these all regions are filled with electrons. These are filled with electrons. So possible tunneling that can happen only in this common region, right? Earlier for maximum it was like this. Okay, EF and EC. So there was a maximum overlap. So the current was maximum. As you increase the forward bias further, this is the situation in which only this part is actually contributing into tunneling. Okay, only these portion electrons they can tunnel, and that's why it will start decreasing. When it will be the minimum, okay, minimum tunneling, tunneling will happen when you have the situation like this. EF, EV, EC. When the conduction band on the N side and valence band on the p side if they gets aligned. Now in this situation, if you see, all these area are actually, these energy states are filled with electrons. Of course this is also electrons. Why there is no electrons in between? Hmm? In between there is no electrons, right? Because this is forbidden region. Between EC and AB, there is no energy states allowed in that particular semiconductor. So there is no allowed energy state, right? And hence the tunneling is not possible. So this is the minimum. Okay. So ideally it should go to 0, but practically it doesn't go to 0. It is like it goes to a minimum value. Okay. After that, if you increase the forward bias further, then it will work as a normal diode. Okay. Just keep in mind why it is not 0, because in case of normal PN junction diode, if you remember, in case of normal PN junction diode also we have situation like this, right? There is no tunneling. However, there is some finite probability that these electrons can overcome this barrier, right? So VBI. So there is some finite probability that some electrons they will manage to, of course, there will be very less fraction, okay, very less. Let's assume 10 to the power minus 10 probability is there. So out of 10 to the power 18, only 10 to the power 8 will be able to pass this junction area. Okay, but there is some finite probability. It's not zero. That some of them they will be able to manage this barrier potential. They will actually pass over there. Or if some electron hole pair at elevated temperature, if some electron hole pair are actually being generated in this junction region, of course, one electron and one hole. So electric field over here it exists in this direction, right? Due to built-in potential. So of course, uh, so that will actually it will pass in this direction. It will pass in this direction. So there will be a net current in this direction, right? So that's why it is the small diffusion current you can say, that is because of that it will not go to 0. After that it will follow this line, okay, as a, so this part is normal PN junction. So this is the IV characteristic of a tunnel diode. This maximum current is called the peak current, IP, and the voltage at which this happens is called peak voltage. And the current at this minimum or in this valley, it is called IV, valley current, and this is called sorry VV, okay, valley voltage. Now the region between VP and VB, that is of quite interest because this is not a normal IV characteristic. Okay, if you see, if IV characteristic is something like this, so what is the resistance in this region? So resistance R is equal to delta V by delta, right? So delta V is positive some number Okay, and delta I, that is negative. It is current is decreasing, so is equal to negative. So this shows a negative resistance region. Of course, if your E is equal to IV, okay, if that is positive, that means power is being dissipated inside the device, and if it is negative, that means it is working as a source, not as a sink. So that's why generally this tunnel diode, they are used as a microwave source. Okay, because of tunneling, the speed is quite high, right? So electron transition from one place to another place, this is happening because of tunneling, which is quantum mechanical phenomena, and that takes no time almost. Okay, but overall, the from electrode to electrode, generally this tunnel diodes we are having uh, delta t transition time that was of the order of uh, few picoseconds, few tens of picoseconds. Okay, few tens of picoseconds, and that's why these devices could be used in gigahertz range. The operating frequency that can go to tens of gigahertz. Okay, so for many microwave applications, the band generally starts from in gigahertz range, right? And 5 6 gigahertz above that, above GSM band, we have the microwave applications. So there generally this tunnel diodes was used, but nowadays there are many devices which have this delta T because of the small size of the MOSFETs itself. Okay, they can give you delay time of actually few tens of picoseconds, right? IT. So these tunnel diodes are generally sometimes it is also characterized with this ratio IP by IV. IP by IV, that is one of the figure of merit of a tunnel diode. Merits of tunnel diode. Okay, so if this IP by IV is more, this implies that the negative resistance is high, right? Because if you see from this equation delta I, so this slope with that will be even higher. Okay, in very small delta I, you will get that. Sorry, negative resistance. Yeah, delta V by delta I. If delta I increases, and hence this will be a negative small, yeah. So that will decrease. Sorry, that will decrease. Now let us see what will happen in reverse bias case. Okay, so we have already seen this. Okay, technically you can also find the peak voltage and value voltage. How to find what will be the peak value voltage? Hmm? The peak is when this EFN that was exactly equal to that aligns with this EV. Okay, so the forward bias required at that time, that will be equal to of course this much. Okay, so this corresponds to the anyway whatever the voltage required for to bring this Fermi level over aligned with EV, that is corresponding to VB. Okay, so in terms of peak voltage, you can say that it is equal to uh, EV minus E, sorry, EC minus EFN upon Q, because this is the amount by which we are increasing it. 1 minute. So let me derive one expression. Even though in books you will not find uh, these equations, but analogically you can. So let's say it is EC, EV, EC, EV, EFP, EF. So this was at zero bias condition, right? Now if this here these are filled with electrons. Now if you move it and align it with this one, right? Then only you will have maximum uh, current, assuming that both are actually same. Okay, let's assume both are equal. But if not, then you will have to see when actually the maximum overlap is there. So this is shifted by how much? Shifted by same, right? EC minus EFN or EV minus EFP. So right, P is equal to EV minus EFP upon Q. That is the correct answer. Okay, and when it will be minimum? When the conduction band reaches over here, EFN reaches over here. So the value voltage that you can derive as uh, so this is going how much? This distance it has covered, and plus this distance also, right? So it will be, ideally speaking, magnitude of EV minus EFP and plus magnitude of EC EFN minus EC N side. This is on P side. Divide by Q. So both of these, if you just add them up, that will you will get value voltage. Anyway, it is not that much required at the undergraduate level. However, you can see that VB and VP are. Now that is also true that if they are not equal, these magnitudes they are not equal. Okay, then this peak position that will not be very sharp, but it will be very broader. Okay, you go through the first analogy and you will find that this will not be very sharp. If they are exactly equal, that will be very sharp. Okay, otherwise it will not be sharp, it will be broader like this. However, it will follow the same diffusion in case of forward bias. Generally, this potential is around, peak voltage is generally 0.50 millivolts. Okay, for silicon it is generally 50 millivolts, and this one is around 100 or yeah 80 to 100, 80 to 100 millivolts. Okay, and generally this forward region that starts from, so when we call it as a very forward bias, very good, 0.5 volts, it is 0.1 volt. Okay, in negative direction the current will be like this. Okay, it is unlike normal PN junction where the current goes like this. So this is the normal junction diode characteristic, where actually this is saturated and it gives you reverse saturation current. In case of tunnel diode, it increases with reverse bias also. Why? So if you had this situation, right, this was the on the P side, this was the Fermi level on N side. Now if you give a little reverse bias, the whole system will shift, right? So that will not be aligned, but it will shift. It will shift down. So let me shift it. Let us shift it by some amount. Okay, this situation. So now there is a reverse bias of this much amount. In that case, if you see, these areas are filled with electrons. These areas are also filled with electrons, right? Now the tunneling will go from this side to this side. So this is one electron that will tunnel, because there is a plenty of energy states in the conduction band. Okay, only this is the forbidden band, right? This is forbidden area. Otherwise, energy states are there. It is vacant. That's all, and that's why these electrons will tunnel. And as you keep on increasing, more and more area will come where the tunneling can happen. And that's why as you increase the reverse bias, the tunnel current will increase. So this is the complete IV characteristic of a tunnel diode. The symbol for tunnel diodes are generally like this. Okay, like this. This is the tunnel diode representation, while the Zener diode is represented like this. Like this. So this is the input P side, N side, whatever you can understand. I think I have completed this topic. If you have any questions, you can ask me in the chat box.